Okay, so good afternoon to all. Let's start today's session. There is a general information. See, all the experiment and assignment date is extended. So I request all of you. So those who are pending to submit any experiment or assignment, they can submit the experiment or assignment in a canvas. Okay, as early as possible. Wait for the 1 minute. There is some issue regarding the lecture. I think you see the two lectures parallel. So there are some issue. Wait for the 1 or 2 minute. Okay, so let's start the session. So I think Is no issue now. All of you having a lecture of DF. So again, see, uh, I request all of you see the date of all the experiment and assignment is changed in a canvas. So those who are pending to submit the experiment and the assignment in canvas, so submit it as early as possible. Okay. So now in last session we starting topic which is the converting AOI logic into a NAND logic and NOR logic. So suppose we have a sum of the equation, so we can make that a logic function easily by using AND gate, OR gate, and invert gate. Suppose in a function we have to do the multiplication, so for the multiplication we can use the AND gate. Suppose in the equation we have the addition, so for addition we have the OR gate, and for invert also you can say the bar, we have an equation like a bar b c plus b a bar c something. So for invert we have a NOT gate. So any function we can make by the first AOI logic, and then that AOI logic you have to convert into a NAND logic and NOR logic. And why it is necessary? Because in some of the example of a KMAP, okay, the example like this, reduce the KMAP and implement the answer by using NAND logic only, or implement the answer by using NOR logic only. So for that time, when you have the equation, you have to implement that answer by using AOI logic, which is AND, OR, and invert logic. Okay. So for that, you have a function, you draw that function by using AOI logic, and after that, you have to convert that AOI logic into either a NAND logic or a NOR logic. So that's why we have to learn this topic. So for that, we have to certain rules. Suppose you have any function, so we can not directly draw that function by using NAND logic or no logic. So first of all, you have to draw the AOI logic for the given function, or you can say by for the given Boolean algebra or given equation. Okay. So first you have to write down the equation. Okay. So from that equation, you have to draw the AOI logic by using AND gate, OR gate, and invert gate. Then you have to select, either you have to implement that AOI logic into a NAND logic, or you have to implement that AOI logic into a NOR logic. Okay, so you have two options, either implement by it by using NAND logic or implement it by using NOR logic. So suppose you are selecting NAND logic, or you are not selecting. In KMAP, the example is given and they are asking to implement by using NAND gate, only NAND logic. So you have to implement your answer by using only NAND gates. So how can you implement? So first of all, you have to draw the circuit by using a simple AND or an invert gate. So AOI logic. Then if you have to implement that answer by using NAND gate, so what you have to do, you can see here. You have to put a circle, or you can say a bubble, at the output of each AND gate in your circuit, and at the input of each OR gate in your circuit. Okay. You have to put a bubble. Now what is bubble? Bubble is nothing but it is simply a NOT gate. Okay, it is simply a NOT gate. So what you have to do, you have to implement your answer in AOI logic. So you are implement your answer with AOI logic. So you have an AND gate and OR gate in your answer. So what you have to do now, you have to put a bubble or a circle at the output of each AND gate, and at the input of each OR gate. if you have to implement it by using NAND gate. If you have to implement it by using NAND gate, okay. But suppose now you have to implement it by using NOR gate. Then what you have to do? You have to do the reverse thing, which you are doing for the NAND gate and NOR gate, okay. So what is reverse thing? In NAND gate or NAND logic, you are putting the bubble, sorry, you are putting the bubble at the output of each AND gate and at the input of each OR gate. Now you have to do the reverse thing. For the NOR hardware, you have to put a bubble at the output of each OR gate and at the input of each AND gate. Okay. So the place of bubble will be changed. For the NAND logic, we have to put a bubble or a circle at the output of each AND gate and at the input of each OR gate. And in NOR circuit, we have to put the bubble at the output of each OR gate and at the input of each AND gate. So this is the simple thing. Then what you have to do? We are putting the bubble extra. There is no bubble in the circuit, but we are putting. So what we have to do? We have to add or subtract inverter on each line that receives a circle. We have to add or subtract an inverter on each line that receives a circle, because the circle is not there first. We are putting a circle to make it an AND logic or a NOR logic. Okay, so we have to add or subtract a inverter which receive the circle in step 2 and 3 here. That the polarity of signal on those lines remains unchanged. Why we are add or subtract an inverter? If we are not adding and subtracting by using an inverter, then the function will be changed. So to remain the function as it is, we have to add or subtract a circle. Then we have to change all the gates. Suppose if you are selecting a NAND logic, then convert all the remaining gates into NAND. And if you are selecting a NOR logic, then convert all the gates in a NOR. Simple thing. And eliminate the double inversion. Suppose you have a 2 NOT gate in a series with. So there is a NOT requirement to connect 2 NOR gate in series. Okay. So you have to eliminate that double inversion. Okay. Okay, let's say this is my circuit. Okay, and I have to implement this circuit into a AOI logic. Okay. So what is the rule for that? You see in a circuit we have a AND gate, OR gate, NOT gate. So this is the AOI logic, because in which we have AND gate, OR gate and NOT gate only. Now suppose I have to implement it by using NAND logic. So what is the rule to implement this function by using NAND logic? We have to put the bubble at the output of each AND gate and at the input of each OR gate. Okay, so you can see. Put a circle at the output of each AND gate and the input of all the OR gates. So this is the output of AND gate. These are the 2 inputs of a OR gate. Again, we have a circle here, you can see, and we have a 2 circle here. Now we have to add or subtract an inverter to each of the lines that receive only 1 circle at input, so that polarity remains unchanged. So we have to add an inverter to each of the lines that receives only 1 circle. that receives only one circle at input so that polarity remains unchanged. What that means, you can see here. Now this line only gets one circle. So we have to add a NOT gate inverter here. We have to add inverter here also. This line also only having one circle, one bubble. So we have to add inverter here. But this line, you can see, in this line we have two bubbles, one here and second here. Okay. Let me draw it. We, in this line, here to here, we have two bubbles. So that two bubbles cancel out each other. Okay. So see here, we are putting two NOT gates here. We are putting one NOT gate here. This line also take only one bubble, so we are putting a NOT gate here. But this line we do not have to put a bubble because in this line we have two bubbles. In this line we have two bubbles, so they are cancel out their effect each other. And now convert all the gates into an AND gate. So these two NOT gates are converted into AND. This AND gate converting into NAND, this AND into NAND, this NOT into NAND, this NOT into NAND, this NOT into NAND. So all the remaining gates here, how many gates we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Convert all the gates into an AND gate. So this is your final circuit. So you can convert AOI logic into a NAND logic, just you have to focus on the rule. Okay. So anyone having any doubt in this? Anyone having any doubt? You can ask me by unmute yourself, or you can ask me a question in chat session. Same thing you can apply for the NOR logic only. NOR logic also. What is the change when I have to apply in a NOR logic? Okay. What is the change? See, what is the rule for the NOR logic? Let me tell you about it. The rule for the NOR logic is we have to apply the bubble at the output of each OR gate. So now we have to put bubble here, I have to put bubble here. And at the input of each AND gate, so I have to put bubble here, I have to put bubble here, here, and here. Now you can see these two bubbles are cancel out their effect. So we do not have to put a NOT gate extra. But here I have to put a NOT gate in this line to cancel out the effect of this bubble. Same way I have to put a NOT gate here to cancel out the effect of this. I have to put NOT gate here also. Like this. And I have to put extra NOT gate here. Now this is my circuit. Now convert all the gates you can see into a NOR gate. Okay, convert all gates into a NOR gate. Okay, then it will be made into a NOR logic. Okay, so this is the simple thing what you have to do. I I think the same circuit we already see. See, here we can see the same thing which we are doing by using NAND gate and NOR gate. First of all, we have to draw the AOI logic. First of all, we have to draw the AOI logic, and from the AOI logic, either you have to select, either you have to make a NAND logic or you have to make a NOR logic. And from that, you have to select, either you have to put the bubble at the output of AND gate or the input of AND gate. Suppose if you are selecting a NAND logic, then you have to put a bubble at the output of each AND gate and at the input of each OR gate. And but suppose if you are selecting a NOR logic, then you have to put a bubble. Then you have to put a bubble at the input of each AND gate, the input of each AND gate, and at the output of each OR gate. Now that you have to decide or you have to select. Okay. So anyone having any doubt? So I think no one having any questions, so I think it's clear. So let's move further. So this adder and subtractor, half adder, full adder, half subtractor, full subtractor is already covered. Binary parallel adder, binary parallel subtractor is also covered. Now an adder subtractor. Now next one is the look ahead carry adder. Now what is the application of the look ahead carry adder? Okay, suppose just to learn about the binary adder. Suppose I am giving the input directly here. A1, B1, A2, B2, A3, B3, A4, B4 is directly given here because we have the value. But once the A1, B1 and C in summation is not done, the summation of A to B2 will be not started, because when we are adding these three, we have generated C1. And C1 is the part of a full adder 2. Then we have add these three, A2, B2 and C1. Then C2 will be generated. And before that C2, we cannot add this A3, B3 or full adder 3, because this C2 is also part of a full adder 3. So it having some time delay. It having some time delay. And we do not require that delay. Then to remove that effect, we have to use the look ahead carry adder. What look ahead carry adder does? It calculates the carry before the process. Okay. So what is that? The speed of the process by eliminating the ripple carry delay. Okay, that carry is rippled to the next full adder. So there is some delay. So what is the application of the look ahead carry adder? In look ahead carry adder, we do not have that carry delay. So look ahead carry adder is faster than the generalized adder, which we see binary parallel adder. Okay. Instead of binary parallel adder, the look ahead carry adder speed will be faster. So in the case of parallel adder, the speed with the which in addition can be performed is governed by the time required for the carries to propagate to the next bit or next stage. So in a look ahead carry header, we are speed ups the process by eliminating the that propagate carry, or you can say ripple the carry delay. So instead of the a simple parallel header, we can use the ripple look ahead carry header. So the method of speeding up the addition process is based on the carry generate and carry propagate function. So we have two functions here in a look ahead carry header, which we can say carry generate and carry propagate. Okay, now what that means, we can learn that one by one. So consider one full header stage, say the 9th stage of parallel header shown in below figure. So this is the end stage. Okay, this is the generalized figure. This is the generalized figure of the parallel header. This is the generalized figure of the parallel header, you can see. So the parallel header are made by the two half header, as we all know. So this is my half header one, which having input A and BA. So we have two options. So AN into BN. So this is the carry which is generated. What this is? Generated carry. If you remember, the carry is derived by the AND gate, and the sum is derived by the exclusive OR gate. So this is the symbol of exclusive OR, and this is my sum of symbol of AND gate. So this is A and B, and so this is GN, which is carry generated. Another half header. So this is final sum, and this is Pn, which is propagate function, you can say, and this is carry generated function, which will give the final carry. Once you see the equation, you can easily understand. Let it be. Okay, from the figure, what you are doing, what you are getting, ascent. What is ascent? Here, AN exclusive or BN, we are denoted by PN. We are denoted it by PN. And Pn we are adding with a Cn. So instead of An, B, and Cn, we can write down Pn plus Cn. We can also write down Pn plus Cn, where Pn, what is Pn? Pn is the An XOR Bn. Then Cn plus 1, which is finally carry here. What's that? That is the equation of An exclusive or Bn coming from here into Cn plus An Bn, which is coming from here. So instead of An exclusive or Bn, we can write down is Pn Cn plus An Bn. And what is here Gn? Gn is nothing but An Bn. Okay, you can see here Gn. So this An Bn is my Gn. Let me write down here only so you can easily understand. This is my Gn. You can see here. And what is this? It is Pn and Cn. So this is the equation of Sn and this is the equation of final carry. So this is the equation of final sum, this is the equation of final carry. So it's that possible to express the output carry of a higher significance stage in terms of applied input variables AB, which is AB, and carry in to the LSB adder. So when my full adder starts working, what I have three inputs, which I already have at the starting. I have three inputs. What? Wait for the 1 minute. Okay, so let's start. What we have in the starting when we are adding. See, once we are starting the adding, we have A1, B1, A2, B2, A3, B3, A4, B4 directly. And the last thing we have C in, which is always 0. So we have these three and all this, but we do not have C1, C2, and C3 at the same instant. Okay, why? Because we do not have C1, C2, C3, because we have to first add this A1, B1, and C in, then C1 is generated, then we have to add A2, B2, and C1, then C2 is generated, then we have to add A3, B3, and C2, then the C2 will be generated, and then we have to add A4, B4, and C3, then we have the final answer. So that delay is known as the propagate delay, or you can say it is a ripple delay. Okay, and why it is generated? Because of the carry ripple or the carry propagate. So at the starting, these three we know. So here you can see which three we have. Now we can assume we are deriving the equation such like, we can also calculate the C1, C2, C3 at the same instant. We can derive the logic, we can generate a logic such like we can get the value of C1, C2, C3 at the same instant, Okay. So what is C2? Okay. All starting with a C1, let's Let me write down what is C1. What is C1? Carry 1. It is here, you can see we have C1 which is G0 plus P0 C0. Okay, we have C1 is equal to G0 plus P0 C0. Now you can tell me, you can ask me a question. What is uh, what can I say? Wait for the 1 minute. Okay. Now you can ask me what is actually G0 and P0. So you can see here what is G0. Let me write down here for you. G0, we have the equation of Gn. So G0 is equal to A0 B0, which is our first input that we have directly. So we have A0 B0 at the very first instant. We have C0 also at very first instant. And what is P0? You can see here. P0 is equal to, again, A0 exclusive or B0. So at the first instant, we have three inputs we know. We have three inputs we know, which is A0, B0, and C0. From A0, B0, and C0, we can generate the C1. From the C1, we can generate the C2. Now, what is C2? You can see here the equation of C2 is equal to G1. What is G1? Now, again, you can say from this equation, what is G1? A1, B1, A1 into B1, that we have. What is P1? P1 is equal to A1 exclusive or B1, that we also have. And C1. In parallel adder, we do not have C1 directly, but now we have C1 also because C1 having this value, which we know. Same way, what is C3? So G2 plus P2 C2. So now what is G2? G2 we have. G2 is equal to A2 into B2. P2 we have also. What is P2? A2 exclusive or B2. But what is C2? So from that equation we are putting here. And we are simplifying the equation. Same way for C3 and same way for C5. So at the same instant, we have all the carries also generated. At the same instance, we have all the carries also generated with us. Okay, all the carries is also generated. And from that, we are deriving some logic, and from that logic, we are drawing this circuit. So this is the circuit of the look ahead carry adder. This is the circuit of the look ahead carry adder. Okay. So this is the look ahead carry header. From that equations, we can draw the logic diagram. Okay, we can also know what is P4. P4 is the B4 exclusive or A4. So we have P4. What is G4? B4 into A4. So we have G4. Same way we have P3, we have G3, we have P2, G2, P1, G1, and we have C1 directly. So we have G1, P1, G2, P2, G3, P3, and G4, P4. And from that, we can already consider what is the value of from that equation, we can derive the value of C2, we can derive the value of C3, we can derive the value of C4, and we can derive the value of C5. So at the same instant, when we are giving the input, the output, final output we are getting at the same instant, irrespective of the parallel adder giving the output with some delay. To remove that delay, we have to use the look ahead carry adder. Okay. So this is the theory of look ahead carry adder. So anyone having any doubt in this? Okay. Combinational circuit, binary to gray code converter is already covered. ECD to XS3 code is also covered. Comparators, so we have 1-bit and 2-bit comparator, that is also covered. Parity generator is also covered. In multiplexer, a 4x1 multiplexer is already covered, but we have some examples. So let's start with the example, how we can easily implement this type of example. And see, this type of example will be asked in either in 3 marks or in 4 marks, or it will be asked in 7 marks, but it will be very easy. Okay. So suppose this type of function we have to given. Function of x, y, z, summation of mean terms 0 to 3, 5. And we have to implement this function by using, okay, we have to check this also. We have to implement it by using 8 to 1 MUX. So what is the meaning of 8 to 1 MUX? We have 8 input and only 1 output. 8 input and only 1 output, okay? So simply we have 8 to 1 MUX. So 8 to 1 MUX having 3 select lines. So we have 8 different inputs, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1. So we know this is 0, 1, 2, 3, 4, this is 5, this is 6, and this is 7. Okay. So what we have to do? This is our function 0, 2, 3, 5. So the mean terms which is given in the function, just write down 1 there. Just write down 1. So we have a mean term 0. So here 1, 2, here 1, 3, here 1, and 5 here 1. And all others remain 0. For all others, put 0. So just we have 8 input D0 to D7, D0, D1, D2, D3, D4, D5, D6, D7. We have 3 select line, which is S0, S1, S2, which is we are selecting as X, Y, Z. Just what you have to do now, and this is our output function. So my D0 is 1 because it is given in the mean term. Okay. Then my D1 is 0, my D2 is 1, D3 is 1, D4, D5, D. Okay, so just what we have to put, the functions which is given in the answer, in the example, at that function we have to just put 1, and all other we have to put 0. All other point we have to put 0, just only this thing. Okay, so this is the example. See, it's very easy. So anyone having any doubt in this? If anyone having any doubt, you can ask me a question in chat session, or you can ask me a question by unmute yourself. Okay, so functions here giving in a function or in an example, we have a function 0, 2, 3, 5. So just we have to make it by 8 cross 1 mux. So we have 8 inputs starting from 0 to 7. And just the mean terms which are given, just put the ones there. Just put the 1 there. So in the mean term, we have 0, 2, 3, 5. So we are putting 1 at 0, at 2, at 3, and at 5. All others putting it 0, and we have to draw this type of logic diagram. We have to draw, or you have to draw this type of logic diagram. Okay, so this is the implement the function by using multiplexer. We do not have to consider all these things. Just take again example. Okay, so from the example you can easily understand. Now again, what is the example? Implement the following function by using 8 to 1 mux. Okay, so 8 input, 1 output. But in function, you can see here how many functions we have: 0, 1, 2, 3, 4. Now we have also 10, 11, 14, and 15. So for implementing this 10, 11, 14, 15, we must require 16 cross 1 mux. We must require 16 cross 1 mux, but we have only 8 cross 1 mux. So what we are doing? So how we can implement this thing? Okay. So do not focus on 8 cross 1 mux. Now just write the table of 0 to 16. So this is the table of 0 to 16. So this is our input A, B, C, D. We require 4 input to write down from 0 to 16, 0, 0, 0, 0, 0, 1 up to 1, 1, 1, 1. Okay. But for 8 cross 1 mux, we only have a 3 select line. So first 3 is our select line, which is A, B, C, S0, S1, and S2. Now what we are doing, we are dividing this in a group of 2. So see, to make it 8 out of 16. Okay. And you can see this is our function. Let me write down here. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So this is my function. This is my function line. So which are the mean terms given in the function? Just write down 1 there. So which are the mean terms? 0, 1, 2, 3, 4. So 0, 1, 1, 1, 2, 3, 4. Then directly 10. So come to the 10. 10, 11, 14, and 15. Okay, so just write down 1 which is given in the function, mean terms which is given in the function, just write down 1 there and put all others 0. Now what we have to do, we have to compare this function with a D. Okay, so you can see, irrespective of a D, either D 0 or 1, my function is all the time remains 1. So f is equal to 1. Next, again irrespective of a D, either it will be 0 or 1, my function is remain 1. So f is equal to 1. Next, here my D is 0, but my function 1. Here my D is 1, but function is 0. So my function is invert of a D. My function is invert of a D, so f is equal to D bar, or you can say D dash. Then again, irrespective of a D, my function remains 0. So my function is 0. In the next stage, again irrespective of a D, my function is remains 0. In the next stage, again from the irrespective of a D, my function is remain 1. Okay, I'll take only 1 or 2 minutes. I know path. Okay, again irrespective of a D, my function is 0. And again irrespective of a D, my function is 1. Okay, we end this session till now. I think all of you now hurry to join another session. We will start our session tomorrow from this point only. Okay, so I request all of you, please write down your enrollment number between 1 to 10. Number between 1 to 10. Okay, thank you. 11 to 20. 21 to 30. 31 to 40. 41 to 50. 51 to 60. 61 to 70. 71 to 80. 81 to 90. 'Now all the remaining, those who have to pending their attendance, please write down your enrollment number for the attendance. And those who already returned, if they want to leave, they can leave the session and join the another session.
Sir,
Yes,
I'm
Niyati.
not able to send my
It's okay. Tell me your enrollment number.
018.
18. Okay.